Let's get started with the last section we're going to cover in triple integrals or double integrals and triple integrals, which is changes of variables. The good thing is that we have already done these. We're just going to do it in a little more general context. So we're going to do, I'm going to start by reviewing changes of variables in single integrals, even though that was previous calculus classes cover that. But then we're going to do changes of variables mostly in double integrals. And then at the end, I'll show you how to do it in triple integrals. So what is a change of variables in single integrals? It's what we knew as U substitution. Remember how U substitution works, by the way, is that we know how to take a derivative of a composition of two functions. The derivative with respect to x will be the derivative of the outside evaluated at the inside times the derivative of the inside. And then if you integrate this and use the fundamental theorem of calculus, what we got for U sub is that if I have a function that looks like this, then what I'm going to do is a change of variables. The change of variables that we do here is call U that function g of x, bless you, and du is going to be g prime of x dx, and that gives me a way of transform that integral into an integral of f prime of u du, which has f of u plus constants as an antiderivative. Okay? And I haven't written in here, but usually if there are limits of integration, then with this change, the limits of integration will also change in this side. Okay? So what I cannot do is to go from here and just do directly the integral from a to b of f prime of x dx and expect that that solution is going to be f of x plus constants. That doesn't work. And the reason it doesn't work is precisely that there is this term in here that was converted to the new differential. Okay? So what is actually happening is, like, if you remember what we did when we did a change of variables to polar coordinates, to change it successfully to polar coordinates, we had to change by a factor for the conversion from one region to the other. And this factor here that appears here, that sort of is hidden in here, because then eventually this becomes f of g of x plus constants. So there is a factor of integration hiding in here that is doing that transformation for you. It's transforming one region to another and then adding in different ways so that the integrals match. Let me show you an example of how this actually works in a practical example. So in here, we are going to use U substitution. What should U be? X squared. So I'm going to pick my U sub is going to be U equals x squared, and then du is 2x dx. Okay. Here I also have limits of integration, so I have to make sure I know those two. So the integral grows from x equals 0, which corresponds to u equals 0, because u is x squared, to x equals 2, which corresponds to u equals 4. So that's going to give me my full u substitution. Also, I don't have a 2 here, but I have an x dx. So x dx is a half of du. And that is exactly where this change of, or this correction factor in the integration is happening. That factor of a half is telling me that when I'm going to integrate in a different interval, I have to count things slightly different so that the integrals actually match. Okay? So if I follow now the u substitution, in u, I have to go from 0 to 4. X dx is a half du, and e to the x squared is e to the u. So now I have a half integral from 0 to 4 of e to the u du, which is a half of e to the u between 0 and 4. That's a half of e to the 4 minus 1. Okay? So that is the solution. But what is happening here, what you should think about, what is happening here is that originally I was integrating in x from 0 to 2. And I changed that interval, that's my region, that I am changing to a region in U that is actually going from 0 to 4 this time. So maybe I should do it a little bit better to scale. So you see that there is, now my interval is much larger in U. Okay? And now I'm going in U from 0 to 4. And to be able to do integrals over 0 to 4, I actually have to multiply by a half, because actually you see there is a 2 to 1 ratio. So if I'm integrating from 0 to 4, I have to make it count whatever the value is, but by a half. So this 1/2 that appears here, which is here, here, and appears eventually in the integral, is what I need to do to correct the fact that I'm not integrating in x from 0 to 2, I'm integrating from 0 to 4 in this interval. That is the same thing we did when we were doing integrals. Instead of on a circle, I changed it to rectangles in r and theta, but then I had to multiply by a factor that corrects what the area is from one to the other. Okay? So we're going to see a bunch more examples, but that is actually what was happening in U substitution. We're actually doing a correction factor because we're doing a change of variables in one variable. And now we're going to be doing change of variables in two variables. But let me start with doing a change of variables in polar. So what is happening here? What integral is this? Do you know what region I'm integrating over? It's the top half of a circle. How do I know? I'm going in x. I'm going from -1 to 1. So let me draw that. 1 minus 1. And then I'm going to go up to the square root of 1 minus x squared. That is the graph of a semicircle of radius 1. So it looks like this. But I'm going from 0. I'm not going from minus the square root to the square root. That would be the full circle. I'm going from 0 to my own hero. So that area. Okay? So that is the integral I'm trying to do. And then I'm going to change it to polar coordinates. But when I go to polar, so what is going to be the region in r and theta that I'm going to integrate over? So r goes from 0 up to 1, because I can go anywhere here from 0 up to 1. But then the angle can go all the way to pi and no farther. So the r is from there to there. The theta is going up to pi. So I am integrating in this region instead. Okay? So that is what's going to happen when I do a change of variables in polar. I'm going to be integrating over a rectangle, but we have to use a correction factor so the two integrals are actually the same. So if I evaluate this in polar, if this is the integral, this integral was now in pi, in theta, up to pi, in r up to 1. Now I have to integrate the square root of x squared plus y squared. That is r. Okay, so this part here, the function itself, is r. And I have to multiply by an extra r to correct that I'm integrating in a different region. And that is actually the difference is going to be sort of the difference in area is measured by that r. Okay, the difference on how I'm integrating. So let's. I don't want to actually integrate it, but I want to tell you what is happening in that integral. So this is going to be 0 to pi at 0 to 1 r squared dr d theta. Okay, so the change of variables in polar, we are going from a region in Cartesian in x and y. We are going to a region in r and theta. Okay, so there is a region here, and then there is some region here. And what we're doing is a map that goes from here to here that we're going to call t. And the map is the following. For any point here that is given by an r and a theta, it's giving me a point here that it maps to. And we remember that x, so this is going to be x, y. But remember that we know how to find x from r and theta. It's r cosine theta, and y is r sine theta. So the coordinates of that map are like this. So it is sending one point in r and theta to a point in x and y. And this map goes both ways. I could go back in my integral, and it starts from an integral that they tell me is in polar, and then translate it to an integral that is in Cartesian. So if I know this region, I can translate it back to a region in Cartesian coordinates also. That is what this inverse map is telling me, is that from coordinates here, I can find the r and the theta for those points. Do you know what is the formula for r in terms of x and y? The square root of x squared plus y squared, we know that is r. Now, what is the formula for theta if I know x and y? The tangent of y over x. So that is the way we transform one region to the other via transformation that gives me from a point in r theta, a point in xy, from a point in xy to a point in r theta. We're going to do this in much more generality. We're going to have many transformations that look like that. Okay, so I'm going to have a transformation. So these are coordinates in here. We are using xy coordinates. In here, I'm going to be using uv coordinates. And this is going to give me a transformation such that t of u and v gives me xy, and an inverse map that given xy gives me what u and v are going to be. They're sort of not so easy in that there will be some function of u and v, so there will be some function of u and v, and some function of u and v will give me the x and the y. And then there is some other functions, let's call them h of x and y and k of x and y, that will give me how to go from one side to the other. Okay? We're going to have very concrete examples, but you should keep in mind the polar coordinates as the main example, where these are the equations of the transformations to go forward and back. Okay? So given those transformations, we're going to have to see how regions transform under those transformations. So for example, I want to show that the change of variables, x is u over 2, y is v over 2, sends the unit square in the first quadrant to a square of side length 2. So first of all, what is the transformation that we're talking about here? This is giving me what x is in terms of u and v. So this is x is u divided by 2, and y is v divided by 2. Can I invert this? To invert this, what I would do is solve for u and solve for v in terms of x and y. So here you can see that if I solve for u, u would be x divided by 2, and v would be y divided by 2. No, I would see that u is 2x, and v is 2y. Okay, so the inverse map, in this case, is going from x and y's, and is giving me 2x, 2y. So that is how the regions are going to be transformed, and they give me one of them. They say, okay, so we're going to go from in x and y, in the first quadrant, the unit square. So put a 1 here, a 1 here, a 0 here. So this is my region. And I want to know where is it being mapped. And they tell me it should be, by the way, from xy to uv's is t inverse. From uv's to x and y's is t. So I want to know what is happening in u and v. And they tell me that apparently it's going to be up to 2 in u and v. So a larger square. And I want to know how that works. So let me show you how I figure out that this is correct, that this is being mapped under this map to this, or that this is being mapped through this to that. So let me start over here with x and y. So, so if I have the unit square, and I'm going through the map that is going to send this to the UVs are going to be 2x, 2y. Then what do I know about x from here? I know that x is between 0 and 1. And that tells me that, because of this formula, that u will be, or that u over 2 has to be between 0 and 1. And that in turn tells me, if I multiply by 2, that u is between 0 and 2. Okay? And similarly, y is between 0 and 1. You can see it here, because it's a unit square. And that tells me that v divided by 2 is between 0 and 1. And that implies that v is between 0 and 2. Okay? So the image of this map will be somewhere in, like what they said, that the u and the v will be between 0 and 2. So it will be somewhere in here. But let me just verify that actually sides go to sides. So for example, take this side here. What side is that? This is the side that x is 0 and y is going between 0 and 1. Where does this go? Through this transformation. Through that transformation, it's telling me that it will go through what we call T inverse. It will go to x is 0. So that means that u is 0 from the defining equations up here. And also, it will tell me that v, or again, v divided by 2 is between 0 and 1. So it's between 0 and 2. So this side over here goes to what side? This is u is 0 and v is between 0 and 2. So this maps to here. Okay, so this whole thing is being mapped. This side is mapped to that side. And you can do for every pair for every side, you can figure out where it goes just to have a sense of what the image is. I think with these equations, it's already telling me that the image is the square of side length 2. But you can check, for example, what happens to this side over here. This side over here is when y is 0 and x between 0 and 1. And then through t inverse, which is 2x, 2y, that is being mapped to v is 0 and u is between 0 and 2. So this map here, this side here, will go to all the points that are here, and so on. So we actually are going to get every point in the square of side length 2. Okay? So we're mapping a region to another region, and they are two mapped to each other. And now let me compare what happens if I actually do integrals over those two regions. So if I did a change of variables, suppose I want to find this integral, okay? And if I did a change of variables to make it easier on me, if I try to do a change of variables like we did in U substitution, but if in U substitution I forgot to do the g prime of x part, I know I would get the wrong integral. So let's try to do an integration without using any correction factor and see what happens. So here the U substitution would be, I want to make this integral simpler. So I'm going to do, instead of 2x, I'm going to call u 2x, and v is 2y. Okay? Then you see that this function would go to this function over here, which is a little simpler. Now I have to modify my limits of integration. So I actually have to figure out what region is mapped to what region. This region is the square interval, the square of side length 1. And we saw that the new region of integration is a square of side length 2. And that is what this is doing. That integral in u and v is telling me I'm going to integrate over the entire square of side length 2. What I'm going to show you is that I'm going to be off. The two integrals are not going to be the same after that change of variables. I would need an integration factor to make sure those two agree. And we'll see what the integration factor is by comparing. So let me integrate first from 0 to 1, 0 to 1, e to the 2x plus 2y dy dx. How do we do that integral? I love that. Let's split up the e's. E to sum is the product of the e's, which I suppose that's what you mean. So I can actually rewrite this as e to the 2x times e to the 2y dy dx. And now I see that it's a function in x times a function in y. The function in x does not change with respect to x, so I can treat it as a constant and integrate. But in fact, we know a trick. That is, when you have a function inside the double integral, there is a product of a function in x times a function of y. That is the product of integrals, which is a very useful trick, because this is going to be now the integral from 0 to 1 of e 2x dx times the integral from 0 to 1 of e 2y dy, which is exactly the same integral now. I just changed the name of the dummy variable, right? So I actually only have to do it once and then square. Perfect. So this integral, let me do it over here. The integral from 0 to 1 of e 2x dx will be e 2x divided by 2 with some u substitution between 0 and 1. So that is e squared minus 1 divided by 2. Okay? So this integral will be this number squared, so I get a fourth of e squared minus 1 squared. And pay close attention to that fourth. That's the key of the whole example. But there is a fourth in front. Let me do the other one now, unless there is a question about this integration. Let's do here this one. So what about if I do the integral from 0 to 2, integral from 0 to 2 of e u plus v dv du? That is going to be, again, I can split it up, and this is going to be the integral from 0 to 2 of e to the u du times itself with a new name. And that is going to be the integral of e to the u is e to the u evaluated at 2 minus 1. This answer is e squared minus 1 squared. Okay? So you can see it right away that we're off by a fourth. What else is off by a fourth? These two squares. This has area 1. This one has area 4. So if I'm integrating in the bigger rectangle, I have to take into account that it's a larger area that I'm putting Riemann integrals on and do a correction factor. So if I was going to do it with this substitution that I came up with, that is going to be okay as long as I multiply by a correction factor, which is the same type of correction factor we use in polar. I just have to figure out what correction factor, and here it's clear that the correction factor is 1/4, not 1/4 factorial, just 1/4. Okay? So I'll explain in a moment how you find those correction factors, but let's try it again. And what if, remember that I was trying to integrate 0 to 1, 0 to 1, e to the 2x plus 2y dx, dy dx. Another possibility that you might have come up with if you're trying to do some change of variables is, what if I call x plus y equals u so that the integral inside just becomes e to the 2u? Or maybe you could have thought, okay, I want 2x plus 2y to be u, and see what happens there. Then that is going to be a different region. So I want to know what is happening with my transformation if I am transforming the square in x and y via a transformation that is given by x plus y is equal to u and y is equal to v. What transformation is that, by the way? So let me invert it also. So I want to find u is v, and how much is x? In terms of u and v, that is u minus y, and y is v, so this is u minus v. Okay? So the transformation I'm using here is t of uv is u minus v, v, and the inverse is t of xy is x plus y, y. That's the transformation we're working with. And I want to know what sort of region do I get over here. I start from here, and I want to know in u and v, it goes where. So I'm trying to figure out, I'm going to send intervals like I did before, just the borders of the region, just to see where the borders go. And hopefully that will be cutting out the region that the image is going to be. So let's start with this region right here. So that region is when y is 0 and x is going between 0 and 1. Then what is happening with v? V is equal to y, so v is 0. And what is happening to u? U is x plus y. Y is 0, so this is just x. And x is going between 0 and 1, so u is also going between 0 and 1. So this region is actually mapped to the same region over here with 1. Okay, the same interval. Now let's do, let's maybe change colors. In orange, what is happening to that line? That line is x equals 0, and y is going between 0 and 1. So what is happening to y is v. So v is also going from 0 to 1. And what is happening to u? U is x plus y. X is 0, so this is just y. So u is actually going also with whatever v is. So u is equal to v, and v is between 0 and 1. So that is, v can go anywhere from here to here, but the u coordinate has to match the coordinate of v, so that is a diagonal. So now that straight vertical line is going to the diagonal that is above the interval 0, 1. And if you repeat this in other colors, this interval here goes here, and let's say this interval here goes here. So this is the new region that I'm going to be integrating over if I do a change of variables. And I have to describe this new region. So let me try to do that here. So if this was A and this is B, what is the region B? If I was going to integrate over that, I would try to look at it with my head tilted 90 degrees, run in Y like I described it actually, and then let X run, or let U run between those two lines. So this one is better described as an integral that goes, or a region that goes in V between 0 and 1, and then U goes from V to this line right here. That is U equals V, but this line right here is U equals V plus 1. So U is actually going from V to V plus 1. So what this is telling me is that if I was going to do this change of variables, then the integrals would have to change accordingly. So this is describing this square. This over here is describing that parallelogram, like this. And those are what T and T inverse send one to the other. Okay, in this change of variables, where we're using that U is x plus y, and V is equal to y as a change of variables. So remember that this number here was a fourth of e squared minus 1 squared. So I want to know how much is that integral over here. So let's compute that one. Before I do that, any questions about how I found the transformation, the transformed region? You can use your transformation to send over the sides of the region from one side to the other, and that will give you what is the new boundaries of your region. The boundaries are mapped to boundaries, so if you map the boundaries, then you can figure out what the image of the region is. So let me do that integral from 0 to 1, from V to V plus 1, e to the 2u du dv. And it has to be in that order. V is going from 0 to 1. U is going from V to V plus 1. That will be the integral from 0 to 1. E to the 2u is e. I am integrating with respect to u, so this is e to the 2u divided by 2 between V and V plus 1 dv. And that is the integral from 0 to 1 of, at V plus 1, I get e 2 times V plus 1 divided by 2 minus e to the 2v divided by 2 dv. Fun. So now I integrate those, and if I do a u substitutions, or yeah, maybe u is the wrong letter here, but a substitution, then what I get is e to the 2v plus 1 divided by 4 minus e to the 2v divided by 4 between 0 and 1. How much is that? At 1, I'm going to get, there's a fourth multiplying everything. That's promising. And at 1, when v is 1, I get e to the 4, oh boy, minus e to the 2, minus the value at 0, which is e to the 2 minus 1. But that is a fourth. E to the 4 minus 2e squared plus 1. Did I get the same thing? Yes, because that is a perfect square over here. That is a fourth of e squared minus 1 squared if you expand it. But now you can see that I got the same thing. Isn't that amazing? I got the same thing, even though I did some like crazy transformation of regions. What happened? Why is there no difference here? In the other one, we had to correct by a fourth. But here, the correction is just 1. What happens is that that square and this parallelogram, they actually have the same area, right? So the area itself is not changing. It's just sort of like doing things in a different way. But the area is not changing, which is in part of why it's happening that we are not having to put any correction factor in this one, okay? They have the same area. This and this, they have the same area. So that is in part an explanation of why there is not going to be a correction factor in that case. In the first one we did, we exploded the square and made it a bigger area that we were integrating over. And that's why if you're integrating over a much bigger area, you end up having to use a factor to eventually also reduce the size of the integral. In here, the area is the same, so I'm integrating over two regions that have exactly the same area. So sort of like the dA, when we write integrals, the integral of the region 1 dA, the integral of the region 1 dA, the differential is not changing.
How did you know it would be the same area?
This one we can calculate because it's a square of length 1, and this is a parallelogram of side length 1 and height 1. It's the same area. But this is a little bit tricky, and we have to figure out how exactly we figure out those. But let me show you that this sort of change in area also explains where the r in polar coordinates comes from. In the change of variables that is given by r cosine theta, y r sine theta, this would send in r and theta, if I go from r to pi over 4, this rectangle, we know it's being sent back and forth to, in x and y, is giving me a circle of radius r and only a fourth of the circle. Okay? And what is the difference in area between those regions? This one has area, which is pi fourths times r, so pi r fourths. But this one, the area of the entire circle is pi r squared, and we are only doing 1/4 of it, so there is a fourth there. So notice that this is pi r fourths times r. And this r, which is not here, is the conversion factor we use in polar coordinates. Okay, and that's sort of like that change in area between regions is where that r comes from. It's one way to explain why it has to be r. The same thing happens when we do transformation in spherical coordinates. The conversion factor has to do with the conversion in volume from one space to the other. So let me now show you again how to figure out that one region goes to another. by doing again like we did before. So here I want to show that using this transformation, it sends this region to this much more complicated region. Okay, and we're going to do integrals starting from something like this and simplify them. So I integrate in something simpler like this. That's how you would use these transformations. So how do we do that? Let's do like we did before. I'm going to see one side at a time where these sides go. So 1 in green, that is the side that goes with x equals 0, or u is 0 in this case, and v is between 0 and 1. Where does this go through the transformation? You can see that u equals 0 is going to give me that y is 0. And what is the x? When u is 0, the x is given by minus v squared. And in what length? So since I know that v is going between 0 and 1, that tells me, let me just write it here, that x will be between minus 1 and 0. Okay? So what region is that in the bottom graph? In the x and y coordinates, is x is going from minus 1 to 0, and y is 0. So it corresponds to this side here. Let's do another one. I'm going to pick now this side over here, 2. That is the side that v is exactly 1, and u is going from 0 to 1. And let's see where that one goes through the transformation. If I pick v is 1, then x is u squared minus 1, and y is 2u. So that tells me that u is y divided by 2. And if I plug in here, that tells me that x is y squared over 4 minus 1. So the y is going from 0 to 2, and the x is given by that function. So you can see then that it is actually being mapped to this line, because that is precisely x is y squared over 4 minus 1, and the y is going between 0 and 2. And you can do the other sides. Let's do, for example, where is this one going to? That side has v is 0, and u is going between 0 and 1. That gives you that y has to be 0 all the time, and x has to be u squared between 0 and 1, so that side is actually this side. And then in blue, this one will map to this side. Okay? So one region is being mapped to the other, and now I can do integrals using this transformation because I know how to go from one to the other. How would I integrate? How would I write limits of integration in each one of them? This one is the integral simply from 0 to 1, from 0 to 1, du dv. That's easy. No, and then whatever function we're doing here, over here, the integrals would be, how should I integrate? What should I integrate first, x or y? If I do x, if I run in x, then I have to explain what functions are bounding y, and the definition is going to change over here. So for negative x, it's going to be one definition. For positive x, it's going to be a different definition. So I want to go in y, and then you see that this definition for the bounds of y, the bounds of x, are the same throughout. So this is going to go in, I want to go in y first, from 0 to 2. And then in x is going to go from y squared divided by 4 minus 1 to 1 minus y squared divided by 4 in x. That's how I would set up those integrals. And one should transform to the other, except that I have to figure out what is the difference in areas so that I put the appropriate correction factor. But we'll see that in this case is a little bit trickier than just area. So what is the correction factor in general? Or before I go into that, yeah, so to figure out where this shape goes, usually they give me one shape and I have to figure out what is the transform shaped. So what I did is take one boundary. For example, here I can describe that piece of line, and then I figure out where it's going. All those points are going. It turns out they're just going here. But if you take this little line here, they actually transform to the points that are in this piece of a parabola. Okay? So if I was to not just verifying that one goes to the other, I'm trying to find what these are, I would take the boundary and then just map it until I have a complete drawing of the new region.